Okay. We're coming to what's actually my favorite part of the class. Um, because having learned about all the different kinds of algorithms, um, I'm not easily impressed by whatever algorithms I learn about or cover, because a lot of them, like the reasoning is fairly straightforward. I mean, I always like to know what is the main idea behind it, what makes them really work. And I have to say that the QR algorithm is one that really has impressed me. Like when I saw what went into it, and that's what I'll be covering starting today, and then uh, continuing into Tuesday. Um, I as I read about these things as a student, I was really wowed by them. Like wow, that's genius. So and hopefully that's something I'll successfully convey to you all. Um, so in fact, the QR algorithm for computing eigenvalues. So it really was the first general purpose algorithm for doing so, for computing all the eigenvalues, was named as one of the top 10 algorithms of the 20th century. Um, and that list has other better known algorithms like the fast Fourier transform, um, and quick sort is one of them. Um, Also, one that's not really a specific algorithm in its own right, but just the whole notion of approach using matrix decompositions to solve problems, whether it's LE or QR. That viewpoint was named one of the top 10 in its own right. Also, the very first compiler for a programming language, Fortran 1 compiler, was one of the top 10. And the let's see, I can remember all 10. Some of them were not really well known to me, but let's see. Um, the Metropolis algorithm, like from Monte Carlo, is one. Um, there's a number that's right at the top of my head. Oh, the fast multipole method for computing electrostatic potential. That one also really impressed me when I learned about that. Um, so let's see, how many did I just rattle off? So QR, matrix decomposition, multipole, Fortran, quick sort, Metropolis algorithm. That leaves 4 more. Metropolis Monte Carlo was, yeah. Um, dang, I forgot nearly half of them. Okay, I gotta look up the list. Uh, oh, I don't know if I said Fourier transform. So okay, so quick sort, Metropolis, Fortran, multipole. Okay, so
Did you leave off the
that's
Krylov subspace method?
oh, I hadn't mentioned that one. So that okay, so hold on. 20th century. I see there's something posted about it at Cornell. Makes sense. Okay. I'll be oh yeah, Creel subspace method, simplex method. Yeah, of course. Yeah, invented by Stanford professor George Danzig. And then oh, integer relation detection. So okay, yeah. Actually was at Stanford, my advisor, Gene Golub, was he ran a class on the top 10 list. In conjunction with statistics professor there, Percy Diaconis. And I was a teaching assistant. And never one of them felt comfortable covering the Fortran compiler, so they asked me to do that one. And what's funny is that by the time the quarter was over, the two professors hated each other. But so well, Gene made the mistake of making some comment about Professor Diaconis' wife, who was also a statistics professor at Stanford. So yeah. Yeah, that's kind of how Gene was. So not saying anything that isn't very well known in the community, but yeah, so uh but yeah, so it's kind of cool that a few of these algorithms come up in this class. So, but I mean, numerical algebra is underpinning so many things. Uh, Also, the QR algorithm is credited to John Francis, who first published it, but there was I believe a woman in Russia who discovered it independently around the same time. So I feel bad not knowing her name, but I know it can be found. So, but I think her version, both discovered independently, Francis's did come out a little bit later. And I don't know if I told this anecdote, but I know I mentioned in class some of the times, but Francis had he was in industry when he developed it. He wasn't an academic, and he left the field not too long after that. So he had no idea he was famous. In 2007, Gene tracked him down and let him know, but he was famous in this field. So, um, okay, so. The last time, the most basic form of the QR algorithm was derived. That you referred to as QR iteration. And all you're doing is you compute the QR factorization of A. And then you overwrite A with the factors multiplied in reverse order. And you repeat until convergence. And I have convergence in quotes because it isn't necessarily going to converge. Now, let's assume we'll continue assuming that A is real. If A has real eigenvalues, generally this will converge. How rapidly it converges depends on how closely clustered the eigenvalues are. So the more spread out they are, the faster convergence occurs. Okay, but if they're complex eigenvalues, it won't converge completely, but there is some form of convergence that you can still work with. So, okay, 1959 is when. Oh, okay. Oh, I do have it in my notes. Okay, yeah, John Francis put it out in 1959, and Vera Kublanovskaya did so in 61, independently of Francis. Okay, I'm glad I took the time to look that up. It will not, but so that's why. Okay, so so the goal is to compute what's called the real sure form. Okay, so Q transpose AQ is equal to some matrix T, where T is block upper triangular. And the diagonal blocks are 1 by 1 for real eigenvalues, and 2 by 2 for complex conjugate pairs. And I'll just write this down. I said it earlier, but just to make sure it's in your notes. This is only for case where A is real. Okay. All right. Okay. So, now the thing is, I think I might have showed this last time when I was doing some demonstration in MATLAB. That even if you're okay with this form, and there's no reason not to, because once you have this form, it's very easy to pick apart those 2 by 2 matrices and get the complex eigenvalues. If you got to that form, but you continued this process, just cause, the matrix would still change. It would maintain that block triangular, upper triangular form, but the actual entries would still change. So when I say convergence, I want to make even more clear what I mean by that. You would not use, like if I use a superscript k to refer to the kth iterate, that, okay, because that's like A0 is your initial matrix and you keep QR factorizing and overriding it. So these are iterates. And you want the norm of it to be less than some tolerance. That implies that the matrix will actually converge as its entries are no longer changing. That is not going to happen. If the matrix is real, I can see it happening, but okay, but generally it won't. Instead, what you do is you monitor the structure of a matrix in terms of which entries are zeros or non-zeros. And you stop if a matrix is block upper triangular at all. Well, with 1 by 1 or 2 by 2. So once you get something that is of that form, all other entries are negligibly small. So individual entries you can watch for being a little smaller than some tolerance. That's when you're done, because if you use a test like this, you'll be iterating forever. Yeah. Okay. And just to be on the record, this right here about computing Q transpose AQ. Okay. This is a similarity. This is an orthogonal similarity transformation. Orthogonal. Okay, because Q is an orthogonal matrix. Q transpose Q is identity. Because in general, a similarity transformation is something like P inverse AP. But it's orthogonal, transpose is the inverse. And we definitely wanted to keep those kind of transformations because that way we don't want to have to compute the inverse of a matrix ever. And now we don't have to. Oh. Sorry, I just saw your chat message. Well, must have been several minutes ago. Okay. All right. Okay. Make sure I'm not overlooking anything in my notes. Okay. Now, and also the key reason why we're going for real sure form is if A is coming in real, computed Q factorization, well, Q and R are going to be real. I mean, multiply reverse order, that's also going to be real. So you never get something not real from operations like that. Okay. Okay. Okay, I think the last thing I'll write on this board before I erase anything is I want to relate what's happening with these repeated QR factorizations and multiplications to the final format you're going to get. So if we let A superscript 0 equal to the original matrix A, and then you have A K is defined to be QK RK, so that's QR factorization for each iteration. And then A K plus 1 is equal to multiplying those same factors in reverse order. And this goes for K equal to 0, 1, 2, and so on. Then if you stop after n iterations, well, no, m iterations. Who knows how many m will be? Well, presumably n would be proportional to n, where A is the n by n matrix. That's the goal anyway. Then what we have is Q transpose AQ is equal to T, where the matrix T is AM, your final matrix that comes out of this process. But also Q is the product in this order of the M Q's that you accumulated. All right, so Q0 to Q M minus 1. So that's how so this is a real Schur decomposition, not the actual Schur decomposition, but again, a real Schur form. And that's how the matrices from the real Schur form relate to what you did during the algorithm. And as you carry out each QR factorization, you can accumulate these and have that final matrix appear at the end. Okay. All right, so any questions up to this point? Now that 1 page out of 5 is down. Oh, I think we better get cracking. Okay, it's around 20 minutes in. Well, I did babble a lot up front, so, okay. All right. Okay. Now, there are huge flaws or drawbacks with QR iteration that will be addressed. Well, one particular will be addressed today. And really, there's one main issue. It's too dang slow, but I want to point out why it's too slow. So the first problem is each QR is order n cubed floating point operations. And we prefer that entire algorithms are at worst order n cubed, like Gaussian elimination. This is order n cubed per iteration, and who knows, if you're trying to compute n eigenvalues, that's going to take at least order n iterations to pull off. Because we're not going to find all the eigenvalues at once. We generally get them one at a time. So we're talking like an order n to a 4 or worse algorithm. Yeah, so we got to do something about that, and we will. I mean, also, so each iteration is too expensive, and there are too many iterations. In other words, convergence to this quasi upper triangular form, as the algorithm is currently described, is too slow. So today I'll address the first of these issues, and then the other will be addressed on Tuesday. So our goal is in some sort of pre-processing stage. We'll reduce A to some form where QR is faster. And since the goal of QR is to reduce A to upper triangular form, maybe we start with a matrix that is in some sense almost upper triangular to begin with, then presumably that'll make QR faster. But if we're going to do this, we have to preserve A's eigenvalues. Whatever we do has to be a similarity transformation. There's no getting around that. Okay. So there must be a similarity transformation of a form. Okay, so U transpose AU, and we'll call the result H. And the idea is, well, H will have the same eigenvalues as A. So then we can do all that QR iteration stuff on H. But we don't know yet what kind of matrix H should be. What?
We don't know what kind of H is.
Yeah.
So we're aiming for upper triangular. So
Yeah, close to upper triangular in some sense.
that should be enough.
But that's our motivation, but we don't know what to do with that yet. Okay.
So it's not currently upper
No, we don't know anything about it.
triangular.
Yeah, it's, but we're gonna try, we want QR to be cheaper on H than it would be on A. All right. So suppose A is equal to QR, we go ahead and QR factorize A. All right, as for our pre-processing stage. What if we try the following? Set U equal to Q transpose AQ. Because Q transpose A, well, that is R. So why not just go ahead and do that? Like you figure, okay, if R is already upper triangular, and we're gonna multiply that by Q on the right. So if R is already upper triangular, how much damage can multiplying by Q do? Okay. Oops, I'm on the wrong page. All right. So let's consider this one step at a time. Because Q can be written as a product of householder reflections, each one zeroing the appropriate portion of a column of A. Okay. Now, keep looking at the wrong page. Okay. All right. So let's take a look at that process. So if I apply H1A, and that is meant to make all of the first column 0, except for, well, okay, I'm gonna fill in every entry, make it like a 5 by 5 matrix. And I'll be drawing a lot of these matrices, where I use X's to indicate non-zero entries. Which means I'm gonna get really tired of writing X's. I need like a stamp where I can just put X on the board. All right, so that's the first step of QR, householder QR, way back from section 4.2.2. All right, so then, because I have to do a similarity transformation, I have to multiply by H1 on the right also. All right, really, if you want to get figure this as H1 transpose AH1, but a householder is symmetric, so it doesn't matter. Okay, now H1 manipulated all rows of A to make these entries 0. So if I multiply by H1 on the right, that's going to affect all columns. So all that work I just did to zero out a portion of a first column of A, well, I'm back where I started. So I stepped on my own toes. Okay. So let's try something else. Because the thing is, we wanted the first column to be untouched. So we need a transformation that's not going to mess with the first row of A when we apply on the left. So instead, let's choose a householder transformation that will zero all but the first 2 entries of the first column. Okay. Now that can be done by operating only on rows 2 to n. You don't have to touch the first row at all. What that means is when I apply the same household reflection on the right, it's going to operate on columns 2 through n. But my work in the first column is untouched. So that's all I have to do is settle for a little bit less. Okay, so what we can do is we can do something that's like QR, except we zero 1 entry less in each column. So first column, you leave 2 entries behind, second column, 3 entries, third column, 4 entries, and so on. All right. In other words, this is where I use that magic phrase, continuing this process reduces A to what is called upper Hessenberg form, which is actually why I'm using a letter H for this. U transpose AU is equal to H, and Hij is 0 if I is greater than J plus 1. So upper triangular is 0 if I is greater than J, but now we need I to be a little higher for that. So it's a matrix that has this structure for the 5 by 5 case. So that's an example of a upper Hessenberg matrix. And the matrix that reduces Hessenberg form, U, is a product of householder transformations that work on the first n-2 columns of A to reduce to Hessenberg form. Because the last two columns are fully non-zero. Right. Okay. Sorry, what?
You won.
Oh, that should be just you. Okay. Whoops. Okay. All right. Okay, I have the algorithm in the note. It's very much the same. They're very similar to householder QR. You're just zeroing one element less in every column. Now, since this is similar work to what's under QR, the reduction to Hessenberg form requires order n cube operations. But that's okay. You only do it once at the start before you commence the actual QR iteration. Is there any questions about the initial Hessenberg reduction? Okay. So now, let's take a look at unity QR factorization. Of an upper Hessenberg matrix. All right. So let's suppose that we have our upper Hessenberg matrix H and I'll find to go 5 by 5. Okay, now we only need to zero these 4 entries, only one non-zero entry per column. So all we need is, given its rotations, G1 transpose, G2 transpose, up to Gn-1 transpose, to reduce H to upper triangular form, where all these are givens rotations, and GK, its job is to zero H row K plus 1 column K. And it does that by rotating rows K and K plus 1. Now, for an n by n matrix, we only perform order n given rotations. Well, technically n minus one, that's order n. And then each rotation will only affect 2 rows. So order n flops at most per rotation. So in total, computing QR factorization of a Hessenberg matrix requires order n squared flops instead of order n cubed. So we've already reduced the amount of work per iteration by an order of magnitude by this reduction to Hessenberg form. So the overall process got a whole lot cheaper. And when we later find ways to speed up convergence, it'll become cheaper still. Okay. But now there's the last part of this. That is, so to complete the similarity transformation that we're performing each iteration. I can find H tilde to be just going to be okay. If I let Q be equal to a product of these given rotations in that order, so H tilde is Q transpose HQ. All right, but Q transpose H is equal to R, so it really is RQ. So what I'm going to do is I'm going to take this upper triangular matrix R that I just got, and then multiply it on the right by all those given rotations I just used. In that order. So now I'm going to be taking columns and be rotating columns instead of rows because I'm multiplying on the right. And we have to be sure about how that's going to affect the structure of R, because we saw what happened before, where you apply some transformation on the left, you get what you want, then you have to apply it on the right, and it messes things up. We want to make sure that's not happening here. So let's find out. So if I take R, which is upper triangular, times G1. So R is upper triangular. Okay. Okay, this is times G1. Okay, now we have to keep in mind, what did G1 do when computing a QR factorization? G1 is supposed to zero out the 2-1 entry of H. It's by rotating rows 1 and 2. So if we apply G1 on the right now, it's going to be rotating. So this rotates columns 1 and 2. So the other 3 columns will not be touched. So those last 3 columns, I'll just fill them in now. So whatever entries are 0, they still have. But now the big question is, in those first 2 columns that are affected, which entries could possibly be non-zero? Because yeah, the idea is that by rotating columns, I'm saying that each of these columns is a linear combination, some linear combination of themselves. So I need assurances about which of these entries will still be 0. Yeah, but the first 2 entries will almost certainly be non-zero. But everything below that has to maintain still be 0 because you're rotating zeros. or taking their combination of zeros. So, and that's okay, because that matrix is still Hessenberg. So then I apply G2 to these two now. The next two, the second and third columns. And that will cause that entry that I just pointed to is made non-zero by G2, but that's okay. Still Hessenberg. So again, continuing his process. So RQ is still Hessenberg. So if you take a QR factorization of a Hessenberg matrix and then multiply the factors in reverse order, as QR iteration calls for, you still have a Hessenberg matrix. So the savings you get from QR factorizing a matrix that's nearly upper triangle already, you keep those savings from one iteration to the next. Okay, the algorithm, the whole algorithm is given in notes, but there's one point in particular I want to make. You cannot do it this way. If you overwrite H with, like you figure out what G1 is. And then you figure, oh, we gotta apply this in the right anyway, so go ahead and do it. And then figure out the next one, go ahead and do it. That will not work. Reason why is G1, G2, and so forth are determined by what QR factorizes H, the original H. Here you're changing H. So you have to do it in this order. With the original H, you figure out whatever Q's rotations reduced to upper triangular form. And then apply those to your upper triangular matrix on the right. In other words, you must store the given rotations as you compute them. So then you can apply them all at once. Now, storing a given rotation is very cheap. All you need are the CS, the cosine sine pairs. So you're literally storing two numbers per rotation. So there's storage is not a problem, but just make sure that you're getting the correct rotations. Yeah. Because it's tempting to think, oh, I'll just do all the G1 stuff up front, and then I can throw G1 away. That doesn't work. Any questions about this Hessenberg QR process? Okay. Now, suppose you've done the following during a certain iteration. if you have, I suppose I let HK be my Hessenberg matrix after K iterations. And then I go ahead and QR factorize it using a process I just described. And then you compute the next Hessenberg matrix by multiplying factors in reverse order. So what if we have the following, where you examine your matrix HK plus 1, you would examine a subdiagonal entry. So like the entry in column J, row J plus 1. What if it's equal to 0? Now, I have to be careful about what I mean here. It's like a floating point arithmetic. It's never going to be exactly 0. What I really mean is negligibly small. Essentially, it's round off error. That's actually something you really want to happen, because the problem decouples. Problem computing all the eigenvalues. Okay, so now we have HK plus 1 has this block structure, block upper triangular. So even though the matrix as a whole is still Hessenberg. So here we have the first J rows and columns. And because of this one subdiagonal entry being 0, now you can focus on these two matrices independently. So you no longer have to apply QR iteration to the whole matrix. You can continue QR iteration on H11 or H22. For instance, you could focus on H11, make it quasi upper triangular, then turn all your attention to H22. All right. Then you stop when it's no longer possible to achieve a curvature decoupling. In other words, your matrix is in that desired block upper triangular form where all the blocks are 1 by 1 or 2 by 2. And those 2 by 2 blocks, it's not possible to make them upper triangular because they come from complex eigenvalues. So that's what you do. After you do a QR iteration, you have to monitor the subdiagonal entries. Each time one of them becomes 0, say, oh, okay, now I'm going to change which submatrix I'm going to work on. All right. So this takes me to the concept of an unreduced Hessenberg matrix. So a Hessenberg matrix H is unreduced if all of its subdiagonal entries are non-zero. Okay, so in other words, no decoupling is happening. So to take advantage of any decoupling that does happen in your matrix, you should apply each QR iteration to a maximal unreduced block. Okay. So you get idea what I mean. Let's suppose I have a matrix that's Hessenberg, but it has some decoupling. Okay. Yeah. So here, so this is an example of that because this entry in row 4, column 3 is 0. So H itself is not unreduced. So, okay. So what you can do is apply QR iteration to this block, this 3 by 3 block here, or that block right there. Either one would be fine. But this one, no, that is an unreduced Hessenberg matrix technically, but it is not a maximal unreduced block because this entry to the left of it's not 0. You have to go further. All right. Otherwise, because the eigenvalues aren't separated in that case. So.
Or that'd be,
Like if I did that.
no. No,
This
from the second row, below,
second row. Wait,
like for,
I can't tell what you want.
these one. Just the first four,
Okay.
just these.
Let's see. No, because of that entry. Yes, so using that one, because of that the entry below being non-zero, the spectrum isn't separated. Yeah.
Here.
Yeah, so the idea is, if you can view the matrix as block, upper triangular, then you can continue QR factorization, QR iteration on any of the diagonal blocks. But it should be one that's unreduced. So. I mean, it would be technically feasible to take any union of consecutive diagonal blocks and work on that. But that's inefficient because there's already decoupling you're not taking advantage of. Okay. Now, in what time I have left, I'm going to focus on okay. I'm going to focus on unreduced Hessenberg matrices. Okay. All right. First, a less interesting property. So, So first, even though it's the second one I mentioned in the notes, but I just want to get out of the way quickly. Okay. The first n-1 columns, I should say unreduced n by n. That's for matrix. For first n-1 columns are linearly independent. Okay. So. Um. And what that means is the QR factorization is unique. Okay. It had been established previously that QR factorization is unique in the case of a matrix with full column rank. A Hessenberg, unreduced Hessenberg matrix might not necessarily have full column rank, but because the first n-1 columns are linearly dependent, that's enough to ensure QR factorization is unique anyway. Okay. And it comes from the fact that the first column has only 2 non-zero entries. The second column has 3 non-zero entries and so forth. So it's impossible due to the structure, which entries are 0 or not 0, to find linear combinations of those columns that are going to be 0. So, okay. So in other words, the rank is greater than or equal to n-1. Okay. All right. Also, a key thing about this is, I mentioned before, in the case of a rank deficient matrix, we want to use QR with column pivoting. But because the QR factorization is unique, at least the first n-1 columns are okay. The last column might be a linear combination of the rest, but that's okay. You don't have to perform QR with column pivoting. So just the regular Gibbons QR approach is okay. But you're not going to run into any problems. Now, the other property. If I have enough time, I'll certainly be able to state it. I'll have to see about the proof. Called the implicit Q here. That's kind of James Bond in a way. Okay. So first, a statement of it. Let's suppose that the matrix A is n by n. And then you have 2 Hessenberg decompositions of reductions of A. So Q transpose A Q is equal to H. And V transpose A V is equal to G. Q and V are both orthogonal. H and G are both Hessenberg. And we'll also assume that H is unreduced. All right. Now, I'm going to write Q and V, or orthogonal matrices, as column partition. Matrix Q as columns Q1, Q2, Qn, and then V, column V1, V2, up to Vn. Okay. That's all my assumptions, pretty much. So if the first columns of Q and V are equal, So in other words, if the transformation, if the reduction to Hessenberg form start out in the same way, then they're almost exactly the same, that each of the other columns of Q are almost equal to the columns of V. They're just plus or minus each other. Qi equals Vi. Also, that the matrices are equal in absolute value. So it's a kind of uniqueness of the Hessenberg reduction, that if you start out reducing a matrix to Hessenberg form in the same way, and then do different things in the meantime, but still reduce to Hessenberg form, matrices you get will still be the same, pretty much. Also, because H is already soon to be unreduced, and because of this, G will be unreduced also. Okay. Now, I will attempt to prove this in the last 9 minutes that I have. Okay, I think I can do it. Okay. Now, I'm going to relate G and H as follows. I'm going to start with G, and then I'll multiply by V on the left, V transpose on the right, and then I'll multiply by Q transpose on the left, Q on the right. Now, V transpose is A. But Q transpose AQ is H. This, I'm taking V transpose AV equals G and rearranging it, V transpose is A. In other words, I have this relationship. W transpose GW is equal to H, where W is defined to be V transpose Q. And so I have this orthogonal similar transformation that relates G and H. Or put another way, because W is orthogonal, GW is equal to WH. So that's the relationship that I really work with. Now G and H are Hessenberg, W is orthogonal. So now I'm going to look at this one column at a time. So G times W1. So W has the same kind of column partition, W1, W2, Wn. So looking at the first column of both these, G times W1 is the same as WH times E1 to take its first column. But the first column of H is Hessenberg, has only 2 non-zero entries. So this is a linear combination of only the first 2 columns of W. So W1, H11 plus W2, H21. But now let's take a look at this W1. W1 is V transpose QE1, but that's V transpose Q1. But Q1 is assumed to equal V1. So it's V transpose VE1, which is V1. But V transpose V is identity, because it's orthogonal matrix. So W1 is E1. Okay. Because of Q and V having the same first column. So now I'm following the first column of G. And then I fill in W1 equal E1 over here. Okay. Is equal to what's left over here, W2H21. Okay. So let's take a look at what's happening on the left side here. This is multiple E1. There's only one non-zero entry here. G is Hessenberg. First column is only two non-zero entries. So this, only the first two entries are non-zero in the second column of W. So first column of W has one non-zero entry. The second column of W has two non-zero entries, and so forth. So continuing this process, what you get is W is upper triangular. Now, I don't know if this came up as a homework problem. Sometimes I assign it. If you have a matrix that is orthogonal and upper triangular, the only way that can happen. So since W is upper triangular and orthogonal, W must be diagonal. Okay. All right. Okay. So what can we conclude from that? Okay. So if I is not equal to J, then we're just seeing Wij is 0. But that means that W is V transpose Q. So VI transpose QJ is 0. Oops, almost out of time. We're almost done. Also, we have WJJ is VJ transpose QJ. All right, and that's those feeling ones that'll be non-zero. So each VI is orthogonal to all the cubes of different indices. The only way that can happen, so this right there tells us that VI is parallel to QI. But we can actually say more than that because W is orthogonal and diagonal So the only way that can happen is for each of the diagonal entries to be plus or minus one. And since these vectors are parallel and have an inner product of plus or minus one. Actually. So the only way that can happen is Vj is equal to plus or minus Qj. So the fact that W is diagonal reduces each V or Q to one direction of the corresponding vector in your family. Your orthogonality of W restricts these inner products to plus or minus one. So the vectors that are parallel and have an inner product of plus or minus one, they can only have an inner plus or minus each other. Okay. Well, actually, this also stems from the fact that the V's and the Q's are already established to be unit vectors. That's key here. Yeah. Yeah, because V and Q individually are orthogonal. Yeah, so. Okay, all right. Now the Hessenberg matrices, Hij is equal to Qi transpose AQJ. And Gij is similar, Vi transpose ABJ. But because the Q's and the V's are plus or minus each other, that means Hij is equal to plus or minus Gij. That's how we're equal in absolute value. Okay. And that's the end.
I'll combine.
Okay. But any questions from a peanut gallery?
No, sir.
Okay, so then we get to the really cool part of the QR algorithm next time, but this is definitely going to help us make that happen. All right.